Okay, so time to continue on with the combinatorics. So continuing with 6.1 combinatorics. So what I want to do in this lecture is, first of all, just do more examples. And then at the end, or actually closer to the beginning, we're going to start going on through section 6.2. Which is the pigeonhole principle, which I have already discussed once or twice, I think. So we'll just try to go through it again. But the first thing that I want to do is do a bunch of examples. Essentially what we discussed last time was that a bunch of counting principles essentially turn out to be inclusion-exclusion for sets. And we talked about the product rule and the sum rule about how many ways there are to do a task, if you can break down that task in different ways. Okay, just for some warm-up, how many one-to-one or injective functions f from a to b are there if the cardinality of a is equal to 5 and the cardinality of b is equal to 7 or 8? Okay, and the way that we think about this is that an injective or one-to-one function, let's recall, although I'm sure that you recall this, is that f is injective if f of x equals f of y implies x is equal to y. Or in other words, anything that is hit in the codomain B is hit by at most one element of A. Okay, so the way that we think about this is if we want to set up an injective function, let's order the elements of A. Since there are finitely many, we can order them. So A1, A2, A3, A4, A5. And then all we need to do to make an injective function is first send A1 to any element of B. If the cardinality of B is 7, then there are 7 ways to do that, right? So there are going to be 7 ways to send A1 to some BI. And then, once we've sent A1 to something, how many ways are there to send A2 to something? Well, you're not allowed to pick the same thing that A1 hit, so there are 6 remaining options. And similarly, once you've sent A2 to one of the 6 remaining options, how many remaining options are there for A3, the third element? Well, you can't send it to either of the 2 elements that are already hit by A1 or A2, so there are now 5 options. And then 4 options, and then 3 options, right? Here's where the number of options for sending A1, the number of options for sending A2, A3, A4, and A5. So this is the number where the cardinality of B is equal to 7. Similarly, when the cardinality of B is equal to 8, it's very similar. You have 8 options for sending A1, then 7 options, then 6 options for A3, then 5 options for A4, and 4 leftover options for A5. Okay, so this is equal to the number of functions, of injective functions, from a 5-element set to a 7-element set. Okay, so this is essentially just the product rule again, the product rule in combinatorics. Okay, let's do another example. This one's slightly more involved. How many ways of seating 4 people of 10 at a table where a seating means everyone has the same neighbor on the left and the right. Okay, so there are two parts to this problem. The first part of this problem is we need to select 4 people out of the 10. And then the next part of the problem is we need to figure out how many table arrangements are there with 4 people if 2 table arrangements are the same, essentially if they differ by a rotation, right? If you put 4 people at a table and then you rotate all 4 of them together, you're not changing who your left and right neighbors are. So first, how many ways are there of choosing 4 people from 10 people? Well, it's very similar to what we just did above. Uh, the first person that you choose, there are 10 choices. And then if you need to choose someone else, then there are 9 choices. You need to choose someone 8. Next, there are 8 choices. Then there are 7 choices. So 10 times 9 times 8 times 7 is the number of ways of choosing 4 people from 10. So in the first step, I have now selected my 4 people, and there are this many ways of doing it. And now I need to find, so this is selecting 4 from 10. And now let's think about some different table arrangements. I'll kind of draw them. Let's say that these 4 people, I give them numbers 1 through 4. Then here are some table arrangements. 1, 3, 4, 2, or 1, 4, 3, 2, something like this. The point is that this table arrangement, 1, 3, 4, 2, is going to be the same as this table arrangement where I do 1, 3, 4, 2. Here I'm using the cardinal directions to kind of spell out different table arrangements, but these two are the same because they're off just by a rotation by 90 degrees, right? So the only thing that matters is where your right and left neighbors are. So the point is, if I give the 4 people that I chose the numbers 1 through 4, and then I put one of them at each spot of the table, I can always rotate until the person with the number 1 is sitting at the north part of the table. So this is kind of a symmetry. You know, if I have this arrangement, I can say this is the same as 1, 4, 3, 2, and now I have the same arrangement, but with 1 sitting at the top of the table. So once I know that 1 is going to be sitting at the top of the table, there are going to be 3 choices for whoever is on 1's left. So 3 choices. There are going to be 2 choices for who is on the left of this person, and then there's only going to be 1 possible choice here at the end. So I have this many ways of choosing 4 people, and then times 3 times 2 times 1, this many different arrangements where 1 is at the top, and I know that I can always put 1 at the top because, as I said, a seating only depends on having the same neighbor on the right or on the left. So, number of seatings. Okay. Let's do one more example of this sort of thing before we get into Pigeonhole. Suppose P and Q are prime and distinct. Find how many positive numbers less than or equal to P times Q are relatively prime to P times Q. Okay. So I am trying to find if some numbers are relatively prime to each other. once again, it's going to end up being, so sometimes it's easier to count how many integers are relatively prime, but in this case, I think it's going to be easier to count the numbers which are not relatively prime. So which are not relatively prime. And remember, being relatively prime can be described as having a common prime factor. So I can list all of the integers that have the same prime factor of p. For instance, p times 1. This will be not relatively prime to p times q because they share a prime factor p. Another possibility is p times 2. These also share a prime factor, namely p. And I can go on all the way up the list, all the way up to p times q minus 1, all the way up to p times q. These are all of the integers less than or equal to p times q that have a prime factor p. And how many of these are there? Well, there are q of these, right? 1, 2, all the way up to q. And I can do the same thing for q. I can look at all the integers less than or equal to p times q, which have a common factor of q, namely 1 times q. This is not relatively prime to p times q because they share a prime factor q. Also 2 times q, all the way up to p minus 1 times q and p times q. Okay, so here are all the integers less than or equal to p times q that share the prime factor p. Here are all the integers less than or equal to p times q that have a that have the same factor q. Notice that these are all the possible integers less than p times q that are not relatively prime to p times q because you must have at least one common factor. You must share some prime with p times q. And there are p of these. And lastly, notice that there is some overlap between these two. They both share p times q inside these lists. So the total number of integers that are not relatively prime to p times q and are also less than or equal to p times q is p plus q minus 1, right? There are q on this list, p on this list, but I've overcounted p times q. So this is the number equals number of integers not relatively prime to p times q. And now we use our kind of complement rule. If I want to find the cardinality of the integers which are relatively prime, I just subtract off the ones that aren't relatively prime. So the total number is going to be p times q minus p plus q minus 1 is equal to the number of not or yeah, relatively prime relatively prime numbers less than or equal to p times q, relatively prime to p times q. Okay, so these are essentially just a bunch of exercises using the principles that we discussed in the first part of the lecture, namely the product rule, the sum rule, the inclusion, exclusion, stuff like that. Okay, what I'd like to do next is move on to the pigeonhole principle. This is section 6.2. Pigeonhole principle. And this is a simple principle, which I think I've both discussed with you before and seems pretty simple, but has some very interesting applications, as we'll hopefully get to. Okay. Here is the statement. if k is a positive integer and k plus 1 objects are placed into k boxes, then at least one box has two or more objects. Which is very natural. Um, you've got, I don't know, 5 pigeons, and you're going to put 5 pigeons into 4 boxes. If each pigeon got an individual box, then there would need to be 5 boxes, but there are 4. So it's like a one-line contradiction proof. Okay, and we're going to use this pigeonhole for more and more interesting problems. So for instance, a quick corollary is that a function f from a set A to B with the, say, cardinality of A greater than or equal to k plus 1 and the cardinality of B is equal to k cannot be injective. And why is that? Well, essentially, the boxes are now elements of B, and the elements placed inside the same box are, or the way that you place an object into a box is the function f assigns an object, namely an element of A, to a box, which is an element of B. So what should I say here? The objects are elements of A. We assign the k plus 1 or greater elements of A to boxes B in B by the pigeonhole principle. We must have f of x is equal to f of y for some x not equal to y. Otherwise, we would need the size of B to be greater than or equal to the size of A. Okay. Let me get some more paper. Let's do a more interesting and slightly more subtle and more fun consequence of the pigeonhole principle. So as an example, let's show that for any integer n, there is a multiple of n that has only ones and zeros in its decimal expansion. So this is kind of a non-obvious sort of thing. What you're being told is that take any number, then there must be some multiple of it that only contains ones and zeros. Showing this directly seems like a mistake because you immediately have to start talking about, oh, for any prime decomposition. I don't know how you'd start arguing this one directly, actually. But the prison hole, or the pigeonhole, not the prison hole, the pigeonhole principle makes things more straightforward. So proof, take the n plus 1 integers, 1, 11, so I'll call this n1 is equal to 1, n2 is equal to 11. N was a poor choice. Let's call it b1, b2, b3 is equal to 111, all the way up to bn plus 1, which has just a bunch of ones. N plus 1 copies of 1, right? Okay. Now what we're going to do is examine the bi mod n. All right. So essentially, remember what this is going to do is it's going to look at the remainder of dividing bi by n. So for instance, 1 is always just going to be congruent to 1 mod n. I'm assuming n is a positive integer greater than or equal to 1, or greater than 1. b2 is going to be congruent to, let's say, r2 mod n. b3 is going to be congruent to r3 mod n, all the way down to bn plus 1 is going to be congruent to r n plus 1 mod n. Now, let's remember, how many possible remainders are there mod n? The possible remainders mod n are the integers 0, less than or equal to I, less than or equal to n minus 1, right? These are the possible remainders that you can have when you divide with remainder modulo n. And in particular, there are n options, right? 0, let's say n is equal to 3, then 0, 1, and 2. There are 3 options. If n is equal to 6, then there's 0, 1, 2, 3, 4, 5. 6 options. So what I've done is I've produced n plus 1 remainders. By the pigeonhole principle, I must have Ri is equal to Rj for some I not equal to j. In other words, if I make a list of n plus 1 things and I look at their remainders mod n, 2 of them have to be the same because there are only n possible remainders, and I've got n plus 1 numbers that I'm taking the remainder of. So Ri is equal to Rj for some I minus j, which means n divides bi minus bj. Let's assume that I is greater than j, so that this is some positive integer. So n divides bi minus bj. But, or in other words, bi minus bj is equal to nk for some k. But bi minus bj for I greater than j is exactly, is written as ones and zeros, right? Let's say that I'm looking at 1111 minus 11. This is exactly equal to 1100 on the nose. If I do 21 ones, 22 ones minus 13 ones, then the first 13 entries are going to be zeros and the rest are all going to be ones. So what we've been able to show is that given any integer n, there's going to be some two numbers on this list that have the same remainder so that n divides their difference, and then their difference is exactly the number that we were looking for. So this is a really cool use of the pigeonhole principle. I like it a lot. So we've seen two examples. Let's do a slight generalization called the generalized pigeonhole principle. Generalized pigeonhole principle. So if n objects are placed in k boxes, then at least one box contains, and here I'll use the ceiling function, n divided by k objects. And remember, the ceiling function, n divided by k here is some rational number, and then the ceiling just takes the smallest integer greater than this rational number. Okay. Proof. Assume for the sake of contradiction that each box contains ceiling of n divided by k minus 1 objects. Okay. Now I want to examine this number right here, this ceiling of n divided by k. What's going on is I'm doing the division rule. So I'm writing n is equal to qk plus r for 0 less than or equal to r less than or equal to k minus 1, right? This is division with remainder. My remainder's r. I'm dividing by k, and q is my quotient. And what the ceiling function does is the ceiling of n divided by k is going to be equal to two things, I suppose. It's either going to be equal to q when r is equal to 0, or it's going to be equal to q plus 1 where r is not equal to 0, right? When r is equal to 0, then that means that k divides n on the nose, and then the ceiling of an integer is just that integer. And then if k doesn't exactly divide n, then n divided by k is some rational number, and then I take the integer that's bigger than that, which is going to be q plus 1. Right? Think about 7 being divided by 3. What is the ceiling of 7/3? Well, 7/3 is the same thing as 2 plus 1/3, and the ceiling of 2 1/3 is going to be 3. Okay, so there are going to be two cases. Let's do the one where r is not 0 first. So suppose n is equal to qk plus r with r greater than or equal to 1. Then n divided by k minus 1 is equal to yes, this thing is equal to q plus 1 minus 1. Then there can be at most be at most k times n ceiling of n divided by k minus 1, which is equal to k times q, which is objects. But k times q is less than n, because n is equal to k times q plus r. So what I'm saying is, if k doesn't precisely divide n, for the sake of contradiction, I assume that there are only, at most, n divided by k ceiling minus 1 objects per box, and that means that the total number of objects is less than or equal to k times this number. But then the total number of objects is less than the total number of objects that I'm trying to put in. So I get a contradiction. And then similarly, if n is equal to qk, so now assume n is equal to q times k plus 0. And what we're assuming for the sake of contradiction, each box has no more than ceiling of n divided by k minus 1 objects. Then the total number of objects is k times this number, or less than or equal to k times ceiling of n divided by k minus 1, which is less than or equal to k times, what's this thing right here? Q minus 1, which is equal to kq minus k. But kq minus k is less than kq, which is equal to n. So once again, we show that the total number of objects is less than n. Oh, sorry, there we go. Okay, this stuff with the ceiling function is maybe a little bit distracting, but the point is, the regular pigeonhole principle says if you've got 7 pigeons and 3 boxes, then at least one box must have 2 pigeons. The generalized pigeonhole principle says if you've got 7 pigeons and 3 boxes, then at least one box must have greater than or equal to 3 pigeons. There's no way to assign 2 pigeons per box and then still have 7 pigeons that you put in boxes, right? The maximum number would be 6. Okay, so that's the generalized pigeonhole principle. Oh, did I really take up 2? Okay. Let's do some more examples. How much time do I have left? Oh, I have very little time left. I guess I'll do these examples next time. Okay, that's fine. There's some very fun and interesting examples, so we'll do them next time.